Pressure refers to the amount of gas molecules in an enclosed area, how densely or sparsely they are arranged, and how quickly they are moving. When there is a high pressure, it means that the gas molecules are packed together tightly and are moving quickly. A low pressure indicates that molecules are further apart and may be moving more slowly. Of course, in our universe, everything is constantly trying to reach equilibrium. When there's a space tightly packed with molecules, encompassed by an area containing fewer molecules, the molecules on the inside will try to navigate towards the less dense outer region.
Our rocket launcher also has to do with thermodynamics. There are several types of thermodynamic processes. The particular one in which our launcher implements is called adiabatic. An adiabatic process is one in which no heat is added or lost, so all expansion is related to a decrease in pressure rather than an addition of thermal energy.
So we have this rocket that sits on a launcher, and before we release it, we use a bicycle pump to increase the amount of pressure inside the tube. We know that because the pressure inside the launcher is increased above atmospheric pressure, you will have some amount of stored potential energy within the gas. When we reach a set pressure, we will open up the system and release some of the stored energy into the rocket, propelling it to an easily determinable velocity.
By using a liquid displacement test in reverse, we can figure out the volume of the interior of the launcher, which is V1. Then we add to that the volume of the interior of the rocket, which because that is the amount the gas is expanding by, we can call that V2. Our formula can be simplified to just P delta V, where delta V is the amount the volume changes by, and P is the increase or decrease pressure due to the change in volume. So we know the amount of the increase in volume, we can determine the amount the pressure decreases by, and from that the amount of energy transferred into the rocket.
We make a graph displaying the change in pressure and the change in volume, which will allow us to determine the work done. The work done can be found by determining the area under the curve made by the change in pressure and the change in volume. The area can be determined by taking the integral, or closely approximated by using a Riemann sum. For simplicity's sake, however, we will take the average and split the area under the curve into a triangle and a rectangle, which will allow us to more easily find the area.
Once we find the work done, we can apply that to the mass of the rocket to find the velocity. If we apply this velocity into a simple equation, we can find the theoretical distance the rocket would travel.
3, 2, 1.